Thank you everyone for attending today's webinar, Design Considerations for Choosing Between Machined and Wire-Wound Springs, brought to you by Design World Magazine. We would like to thank our presenter, Gary Beam with Helical Products Company, Inc., for being here today. I am Leslie Langnaw, and I'll be your moderator. Just a couple of housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, you can use the hashtag DWWebinar. We will also have a Q&A session after the presentation, but feel free to submit your questions anytime throughout the presentation, and we will ask them at the end. You can find questions on your GoToWebinar screen where it says put in questions. Now I'm going to introduce you to Gary. Gary graduated from Cal Poly Pomona with a bachelor's degree in mechanical engineering. His first professional job was with the Naval Ship Missile System Engineering Station in Oxnard, California, where weather deck hardware was designed and tested. After 3 years there, he went to Cal Poly San Luis Obispo, where he obtained his master's in mechanical engineering. During that time, he was also involved in a work-share position at Lawrence Livermore Laboratory, involved with non-destructive testing techniques using holography. Studies at CPSLO focused primarily upon mechanics and concluded with a master's thesis that developed 3D kinematic FEA techniques used to evaluate automotive suspensions. He's been at Helical now for about 38 years, or a little more than, and closed form and FEA techniques were developed to understand and predict the behavior of single start and multiple start flexures configured from a helix. As I mentioned earlier, Gary will be available to answer any questions you have after his presentation. So without further ado, I'm going to hand over the mic to Gary.
Well, greetings. Hi, this is Gary Beam, and I'm glad everybody's here today. I guess there's 44 of us at this point, so let's get this thing going. The topic here is the ability to be able to choose between machined and wire-wound springs. And this presentation is based upon a paper I wrote called Wire-Wound Springs, Wire Springs versus Machine Springs, a comparison. And you'll be able to get hold of this white paper at the end of this. Leslie will take care of that later on. So, a little bit about Helical Products. It started in '58, '59, and it started as a company manufacturing flexible shaft couplings. Well, those of you who've dealt with couplings recognize these because these have been pretty much a standard of the industry ever since the beginning of this company. But they also look an awful lot like machine springs. So you can see how we've morphed ourselves into the world of machine springs. Helical actually started the machine springs back in 1960, and since then, with the combination of springs and flexures, we've got about 28,000 different flexures created, designed, and documented. And so you can see we've been busy making these things for some time. So firstly, let's take a look at the wire-wound spring. Here's a picture of things you've probably seen throughout your life, and these people have been at this thing of making wire-wound springs for some time. In fact, they've preceded us by a mere 500 years. This product goes way back in time now, and it's been useful to all of us. In fact, even to myself, I know back in the college days, I had a product I wanted to design, and it was a product that had the chance of going forward with a patent and production. and it had a wire spring in it. So I've been involved with and aware of wire springs for a long time before I even know that a machine spring existed. Here we go. And here's a picture of a machine spring. Looks a lot like a wire spring, but there's a major difference. There are attachments in these pictures, and these attachments are one of the big differences between wire and wound springs. And here's a little bit of the same information, but we've got some wire and wound springs side by side. The first wire spring is quite obvious. It's ground enclosed. Second spring in the line there from the left is a single started machine spring, and the third spring is a double started machine spring. All three of these springs have the same spring rate, even though they look a whole lot different. The most important bullet here is that all these springs, wire wound and machined, are manufactured with rather sophisticated CNC systems today, and there is certainly an evolution in both of these elastic forms, and it continues and continues and continues. Okay, here we go. We can get into a few details here about the differences between wire and wound. Precision is one that people like to jump on right away. May not be the most important, because most springs that are made are not of the precision type. It's rather trying to make basic things work. And 10% precision, as you can see here on the top of this list, is available in both wire and machine springs. It's probably the standard of both industries. A 1% spring can be made with wire product, and certainly can be made with machine product. The wire folks accomplish this primarily by sorting, because at some point the process can't be jiggled enough to be able to make 1% every time. But the good thing is that they aren't very expensive, and one can accomplish 1%, or around 1%, with a sorting process. For machine springs, because they're more expensive, we can't throw many springs away and still stay in business. So, but we can make 1% springs and are happy to service those needs. And if we go down to the 10th of percent, it shows that the wire people cannot do that. If there are some of them on the line, they're probably writing notes right now. Yeah, I'm sure it can be done, but it becomes a real trick process at that point. We have also made 0.1% springs, and can do that. It takes, says we're having trouble here. We have to do additional processes to get that 0.1%, and but it can be done, and we have, and those are being made periodically. The materials that are used for wire springs are pretty straightforward. They use high-strength steels, nickel alloys, and even titanium alloys, including stainless steel too. And most of these materials, not all, but most of these materials get their strength from cold reduction, and the wire products are bent to form cold generally, and so this cold reduction actually helps the strength level of the spring. Of course, The wire wound springs can be made in primarily large sizes, and those are hot rolled springs, and of course those will require some heat treating after the processing. Machine springs are made from the list of alloys that are shown there, the corrosion resistant alloys, and for those who have a metallurgical background, you'll say, look at that, they're all wire etching steels, and that is correct. And the reason for that is with wire etching steels, the heat treating is done around 900 degrees, and there is no quenching. There's no phase capturing done. The precipitate comes forward in the alloy as martensite, and that gives the alloy the strength. It also means that the materials don't have to be quenched, and we know that when you quench something, it's a great heat transfer activity, and that can leave residual stresses in material. So there are some other alloys there that we do use, some high-strength aluminum alloys. There's already been a question whether we make titanium springs. That is a webinar unto itself, and would be happy to talk with somebody about that at a later time. But we do make titanium springs, and probably have made one of the large number of titanium springs, certainly in this country. Delrin and Ultim are plastics, and they're machinable, and we can make springs out of those too. That would be a very special activity. The sizes of springs, I can give you some numbers, but here with this time we can kind of get the picture. In the upper left picture is one of our larger, or maybe even largest, machine springs. So that's pretty much as big as we can manufacture. And we certainly know that the wire people can make things way larger than that. In the lower right-hand corner, there's that dime again, and with something that has been a machine spring and manufactured, and that one went to the medical industry. The wire people can make that size quite easily, and probably smaller. It's all dependent on wire size at this point. Okay. So here's some pictures of the attachments in springs. These are compression and extension springs made by Helical, and you can see they're pretty big, good sized, and they have threads on them, and so on. Most of what you see in the picture are compression springs, but where would you see there be some extension springs? And here's a good candidate, and here's a candidate, and even over here is the candidate. Basically, it's based upon the attachment that will allow one to get a hold of it and then extend it. To put machined ends on wire springs, that's an interesting cottage industry that we have bumped into, Helical has, and they can be attached, they can be brazed, they can be welded on, but it always turns out to be a difficult issue, and this is why one might want to turn towards a machine spring. On the left there is a wire wound spring that was used in the aerospace industry, and now that is a machine spring, and no longer are these highly skilled young ladies being used to bend and weld and make those things work. On the right hand side is a machine tool application, I believe, and again there's the same thing. There's the wire product and the machine product. The wire people should not be worried about us taking over their industry, I have to tell you. As far as when you look at the amount of wire springs built versus machine springs built, you could almost argue that there aren't any machine springs built. They probably make many millions to every one that we make. Okay. We know that when you compress or extend a machine spring or a wire spring, that you get the spring likes to rotate. When you compress it, it likes to unwind, and when you stretch it, it likes to wind up. And sometimes that becomes an issue, and one doesn't want that. And you can do this with wire springs. It's a little bit of a game, but the two pictures in the foreground are springs that have right and left flexures in them. And when you compress that, there is still rotation in the spring, but it's in the center of the spring. The two ends stay in line. And so, as you can see, both of those springs have right and left flexures. And this is a way to stop rotation in the spring. And then the big spring in the background is another way of accomplishing this. That's two springs. They're nested. The outer spring happens to have a right-hand flexure, and the inside spring happens to have a left-hand flexure. And there was a design criteria that when the springs deflect, that the reaction, torsional reaction, is the same, and it is, and it nulls itself out so that there is no rotation. So, two ways of dealing with the rotational issue regarding wire or machine springs. Okay. Here we have some torsion springs, and those of you familiar with torsion springs probably pick that up right away. The magic here in the machine spring is the attachment. All the attachments on every one of those springs that are there allow you to put a moment, and we like to call it a pure moment, and I'll tell you why in just a minute. You can put a moment on that spring and then make it deflect in the unwind or the wind-up direction. With wire springs, getting a hold of them is more difficult because you're limited to primarily tangs. Now, if you put a force on a tang, you get a force at a distance, and you'll get a moment, but then you have to resolve that force, or you have free body motion. And for the physicists among us, that means things get to fly around the room, unless you deal with that that force. But with machine springs, you can apply just a moment, and you'll get just the deflection that's desired. And every one of these springs with splines, with holes, with clamps, with cross slots. The spring that's in the furthest right-hand side, the big guy in the second row there, he is almost a standard aerospace interface where there's two pin drive to it, and then 4 threaded holes that hold the engaging mechanism to the spring. Okay, another thing that happens with machine springs that's kind of neat is we're able to put a 2-start flexure on it. This picture and the one on slide number 7, when we started, the one that was on the right, are all multiple started springs. And with multiple started springs, you get a benefit that isn't available to single started springs. And here's what they look like, and we'll talk about that benefit in just a second. Single started spring is common, helical, it can make them. And of course, they're both available in the wire springs and the machine springs. The double started springs, as you can see, are just a helix that starts another 180 degrees from the original one, and progresses through the spring. And then there's a triple started one behind there at the very top. Now let's look at what these things are and why it's important. When you've got a single started spring and you put a force on it, or that force can be compression as shown here in the diagram, or it can be in extension too. Your force is a distance away from the center line of the spring, and of course we know it forces it at a distance to create a moment. And with this single started spring, whether it be wound or machined, that moment has to be resolved. And this sometimes will cause pintles in a valve to wear on one side. It'll cause, depending on the application, it can cause some degradation in the use of the product. In the multiple started springs, and this multiple started spring that we're using for an example is a double start. You can see the two forces, but if you do the math and realize that one of those forces up there is minus, and then you sum the moments, you'll find that the sum is 0. And so there is no moment here that needs to be resolved. And this is in our textbooks that we're used to and so on, there was a squiggly line that was called a spring. And when people are talking about single degree of freedom systems, you just assume it's like that. Well, the only way that can happen is if one's using a multiple started spring. Okay. This is a picture of Helical's website, and these topics we just gone over are also available in little video clips on Helical's website, and you can click this button when you log on, and I'll give you that address in just a minute. And you can see some of these things in action, and so it'll help you to understand some of these concepts if that would be of value to you. Talk a little bit here about linearity of springs. Some people want linearity, some people do not, but usually the desire is there for linearity, or the consideration is that it is linear, and if it deviates from that, it may or may not become an issue. Both wire and machine springs are constructed of a uniformly shaped structural element, which happens to be elastic. However, there is a helix angle involved with this, and the helix angle can be shown here. This is certainly a machine spring, but helix angles are common to both machined and wire springs. And this helix angle influences, or can influence, the linearity. And let's go on here. And so when a wire spring or a machine spring are compressed, that helix angle approaches 0. It goes or reduces. And when you do reduce that, it actually causes the spring to lose a little bit of its stiffness. So that works against linearity. The curve is kind of concave to the bottom from a force deflection diagram, and so you get a reduction in the rate there. And in extended springs, it actually just goes the other way. It causes the spring to become a little stiffer, and so that's one place where linearity gets changed. Okay. In wire springs, there is an issue where on this closed and ground spring, that you get a contact there, and as you progressively compress this thing, that contact moves. In this case, moves around counterclockwise, and it causes a slight change in the linearity. even though the spring element is still available for the torsional shear that is seen, and the actual amount of coil that is there for the little bit that bending applies to linearity in the spring changes, and so the number of coils can change. Now, if you wanted to have a nonlinear spring, which you might do, particularly with wire spring, you can start with a coil that's very close at the ends and then open it up to wide and then go close at the other end, and that will help you get a nonlinear spring. In the machine springs, you can see that the gap at the very end has no contact, and so at least for this reason, the machine spring will give no change. We should talk a little bit about residual stresses. The wire springs are plastically formed, and this forming leaves residual stress in the spring. Now, there are heating processes that can remove some of that stress, but it cannot get it all out. And so we know that when there's residual stress in springs, that the residual stresses have to be overcome before you can get elastic motion in the spring. So with wire product, this is a substantial issue. With machine springs, however, the blank that is started in the process is completely fully annealed, and so there are no residual stresses. So the issue of residual stresses is beneficial to particularly the machine springs. Well, and we should also state here that most of these issues have to do with large displacements. If you're talking about an application where the displacements are very small, the linearity is likely there in both forms in about the same way. And it's only in the large displacements do the changes in linearity become an issue. The other thing the other application that's going on today with springs is that they're being used in dynamic systems, and dynamic systems that have spring mass resonant desires. And the machine spring has proven to be a real benefit in that area. And the two aspects about machine springs that gain us benefits here are, one, the attachments, and whether it be extension or compression or both, are very effective. And also the multiple starts. Multiple starts, again, tend to resolve those moments in them, and when those moments are resolved, the spring moves in a very straight, uniform way and tends not to wander around in its modal shapes. Excuse me, does not wander around in its deflective shape. Modal issues are always an important issue, and they have to be addressed separately for both machined and wire-wound springs. So here's the website for Helical, and you can log onto there, and you can use or not use the www, because both are registered websites, and this pretty much takes us to the end of this presentation. I do thank you so much, and we're going to come forward here maybe a little bit and have some questions.
Thank you, Gary, and the remaining time will be for questions. A couple of questions have come in regarding what types of materials you can make the springs out of. Some questions regarding titanium and carbon fiber, for example. Gary, can you talk about that for a couple minutes?
I'd be happy to. Titanium springs are complicated springs because the material is such a complicated material. But we do make a lot of springs. We have a couple thousand pounds, I think, right now, sitting out on our back bay for getting ready to make some more titanium springs. In titanium, there's two particular materials that are used. One is 6Al4V, and the person that's asking the question is probably much aware of that. The other material that we use and prefer is the 38644 beta C because of its higher strength. But the springs out of titanium become an adventure every time we work with them, because there's always a little difference from the last batch of material. As far as carbon fiber, actually we have not dealt with that. One of the reasons for saying that we haven't is that the stresses in extension compression springs are torsional shear, and those fibers have to be in a direction that would be beneficial to handle that stress. And so we're not aware of any process that will allow us to do that. But if the person posing the question would like to talk to us and share a way to get the fiber in a direction that's beneficial to resolve the stresses in the material, we'd be happy to talk to them.
Okay. One questioner or one attendee is asking whether or not you can give a cost ratio of wound and machined springs, approximately equal size and cross-section.
Yes, I would be happy to do that. The process time for wire springs is in seconds to minutes per spring, and the process time for machine springs is from minutes to hours. And so cost is all about process time, and so to expect a machine spring to be the same cost as a wire spring, it's very unrealistic. Only in some very, very rare situations have we been able to get close to that cost. I think our least expensive spring was somewhere around $3 a spring. So, and we all know that we can buy wire product for less than that.
Okay, and is your data on precision addressing relaxed length or spring constant?
I'm sorry, I had 2 ears active at the moment.
Oh, okay.
Help me a little, please.
I'll repeat the question. So somebody has come in asking that in your data on precision, does it address relaxed length or spring constant?
That's a good question. Relaxed length. We can always modify the length of a spring if it's too long and making it shorter, because we can leave a section to remove to ensure that the length is as precise as someone wants. But most of my discussions were regarding rate precision. So those numbers you saw up there in that chart were regarding rate precision.
Okay. Another question that's come in is, do you have any compromise in spring life, or should they consider any compromise in spring life when they're deciding between machine springs or wire springs?
Things that would compromise life. In wire springs,
do they have to, yeah.
Yeah, in wire springs, when you got closed and ground conditions, you have the chance of some fretting in that area. So that becomes a life-concerning issue. And also, when there are extension springs, you have an interface that can cause trouble, particularly when the hooks and loops are bent. The zone of bending can be a life issue. With machine springs, we have features on the ends that are stress relief zones, and You'll remember from some of the pictures that we had large stress relief holes in the ends of our springs to try to mitigate and give infinite life. But life issues, things that challenge life issues are numerous, and we are always happy to work with people in trying to understand and resolve any such issues that may come forward.
And one questioner was wondering if we could maybe go back a little bit to the cost issue and maybe go into it a little bit deeper about what would be the cost ratio of a wound spring compared to a machine spring.
My goodness. I would think there are times when the numbers could be as 10 to 20 times more, just because of process time. The wire people buy material by the pound. We buy material by the pound. The wire people use all of the spring, all of the material that's used per pound. We machine things away, so we get to throw some of the material out. So the numbers of it can be pretty high as far as comparison.
It depends on the application. It depends on the need.
You know, Leslie, there's another issue that comes forward. Is that when you use a wire spring, it has to be used somewhere. It connects to something and so on. And the same thing with machine spring, but you can often integrate that interface with the wires, with the machine spring, and that can become part of the spring. And so when you compare costs, you have to be careful that you look at all the costs that are associated with one versus the other, because by putting things together in one piece, that there are some cost benefits in doing that. So that helps the analysis and comparison for the machine spring.
Another person has asked, what are the differences between wire and machine springs when we consider surface creep?
Well, surface creep is a function of stress over time. There's only one material that I know that does not creep, and that's 38644 beta C titanium. In fact, that is its strongest suit. We have products that are fully stressed, and I may say fully stressed, 150, 160 KSI stresses, and they sit for 10 years, 20 years, and there is no creep whatsoever. But as far as all the other materials, both wire and machine people have to deal with the same issues.
Okay. The next question is, in general, what's the delivery time frame an engineer needs to consider for a custom design machine spring?
Well, it depends on a lot of things, but we have a full engineering staff to talk with the folks who are thinking about using machine springs. And we can go forward, and we do all this for free, by the way. And it can take a while. I've seen it. In fact, I've seen it take years, but that's not the norm. A norm would be just a few weeks for the design to get resolved, and then we can move into the manufacturing of prototypes prior to a production. Prototypes usually take a few weeks, depending on how complex they are.
Okay. Is there any minimum order quantity limitation?
There is, but unfortunately our prices are high enough that they never get touched. I think our minimums now are at $50 per order. Yeah, for one piece.
Now, are most machine springs custom built to the application, or are there standard designs that an engineer can choose from?
Good question. There are no catalog items at this time, but I'll come back to that. To date, everything we've made has been made to the application, simply because there's millions and millions of ways of making these things different, and we just haven't had people wanting the same thing. We are, however, working on a series of calibration springs, and I think once that comes out, we will have a catalog basis for a spring that will be a target for somebody to design to, as opposed to create their own desire and then come in and ask us to make it to that desire.
The question is, do you have any experience in combustion engine valve springs? And I'm going to guess that, are there any advantages in using machine springs over what they would normally use?
There is, but I don't think anybody's willing to try. I'm a motorhead myself, and I've asked the same question. Machine springs are historically a little longer than wire springs, particularly for compression, and internal combustion valve springs are of that category. So you can't actually use a machine spring for one of those applications if there's already been designed for a wire spring. The valve stem has to be larger. The only benefit that I can see it would be is if you used a multiple start machine spring in that application, the valve in the guide interface, the forces in there, the pressures in there would be reduced, because that moment that I was telling you about earlier will not exist. And so there should be increased valve-to-valve guide life if a machine spring were used in that application. So maybe those people that are running diesel engines and things that are, very long-lived could benefit from a machine spring if the engine manufacturers would be willing to have larger or longer valve lengths.
Okay. In an application, does an engineer need to provide inner or outer guides for machine springs?
Many people do, because there can be dynamics involved in the spring. This thing could be something that's being bounced around a little bit, and so you might want to control it that way. But the springs, because the ends are so square, they tend to stay where they're supposed to be with only minor retention, either on the OD or the ID at the ends of the spring. So it's not a mandatory issue.
Okay. And if one is currently using wire spring in a compression application, can a machine spring be substituted?
Generally, no. And the only reason is because the machine spring will likely have to be longer, and so you won't be able to get the full range of motion out of a machine spring if it were tried to be substituted for a existing wire spring.
Okay. And how do machine springs compare to wire ones in resonant dynamic applications?
Well, that's where the magic is. The multiple start machine springs give you a 1 degree of freedom system, which is usually the goal of those resonant systems. And the coils do not touch each other, so there's no sound and there's no debris generation. So right now, the machine springs are seeing more and more dynamic resonant systems.
Okay, another question. When we calculate valve train assembly, we often assume 1/3 mass of wire spring to dynamic calculation. What can we assume for a machined case?
You can assume 1/3. That's not a bad number, but that is not the exact number. We have computational techniques here that we use that roll that around. I've seen it as least as maybe 28%, and I've seen it as high as 45%. in computational.
Okay. What is the most common industry or application for machine springs?
Well, fortunately, we're liked and used in a lot of areas. So industrial applications are certainly there. There's a lot of aerospace activity. There's a lot of medical activity, and all of these areas are blooming right now. So any place elasticity is needed, a machine spring can be considered.
Okay. Are there any other questions? We have a lot of good ones.
Yeah.
We have about 10 minutes left, so if anybody else wishes to add in a question, feel free to do so.
Leslie, at the end here, you're going to tell people where they can get this white paper, correct?
Mm-hmm. Yeah, actually, I believe, I think it's going to, it will be emailed to them along with the URL link to a recording of this webinar.
Yeah, Leslie, one of the reasons they'll like the paper is because there's a lot more content
Exactly.
there than what
yeah,
we talked about.
It's a nice one. It goes through a lot of good information. Another question just came in. What input is needed from client to inquire a certain machine spring? Okay, what does the client need to tell you?
Right. Well, they need to know what the envelope is that they have available, and they need to know the performance that they desire. And we can, if they log on to our website, there is a procedure form that they can fill out and send it back to engineering at helical.com, and we will be happy to go forward with it.
Okay.
Try to make it easy.
Any other questions for people? I've got one for you. Who makes machine springs?
Well, actually, anybody who has a good CNC machine shop can make them. The trouble is that we've been doing it now for over 50 years, and we've developed processes that make it as efficient as possible. But there are particularly torsion springs I have seen made in other industries, and eventually those people give up and find Helical. But anybody who's got really good CNC equipment, they can try to make these things, and sometimes they can do a fine job. We at Helical are special in the sense that we have this front-end application engineering group that helps people along with the applications. We're 130 people now, so that's a large machining facility, and we're also AS9100 certified, and so we're doing everything we can do to make us as good as we can be.
Okay. Okay. Well, if there are no more questions, please note on your screen that you can email Helical at engineering@helical.com if you would like to ask questions offline. And over the course of the next couple of days, not only will the white paper be emailed to everyone who has registered, but so will the URL. Oh, I have a couple more questions that came in here, and we'll go get those while we can. What are some applications for the plastic springs, and how common are they? And how does the degradation of the plastic influence the life of the spring?
Plastic springs are usually used for non-conductive activities, electrically non-conductive, and magnetically non-invasive, although aluminums will do that too. Some of the plastics are pretty effective for their stress capability, but it depends on what's chosen and what the environment is, because plastics, some of them won't even live well in water, let alone something nasty. So it just depends on what you use. I've listed those two materials that are on the presentation. The Delrin is the first one that we've used a lot of, and the Ultram is another one. Peak materials have been used also. So basically anything that has relatively high strength is a candidate, as long as it's machinable.
Okay. And another question that came in is, can you integrate your technology in an existing product?
I'll do that all the time. Yeah, we're in the middle of some very sophisticated things today, both in the medical world and the aerospace world.
Okay.
And the other thing we can do, this question may be going this way. We can service customers who are actually major machining activities themselves, and they have shops that are needing work to do, or they'd like to, and so we can go through the development of a flexure for them. They can make the blanks themselves and ship them to us, and we can just provide what we call the flexuring or the generation activity, and ship the parts back to them. And so it allows them to use the facilities that they have as efficiently as they can, and only outsource the one process. So that's a term we call generate only. And yesterday I was walking through the shop, and there were many boxes of those products coming in right now.
Okay. Any more questions, anyone? All right. Well, as I was mentioning earlier, those of you who have registered, you will be receiving a copy of the white paper that Helical generously has provided to us, and you will also be receiving a recording of this podcast, of this webinar, so that you can review it again at any time. So I'd like to thank everyone for attending, and thank you, and have a great day.
Helical thanks everybody for attending too. Thank you so much.
Thank you all.